This is Porterville College, Physics 102A, homework solutions for Chapter 10. Starting with number 15, aluminum's density is given. What's the radius of a solid aluminum sphere with mass 10 kilograms? There's density, there's mass. We use the density equation to find that volume is mass divided by density. Since we need the radius, let's convert volume of a sphere to 4/3 pi r cubed. Solving for radius, we get radius is the cube root of 3m over 4 rho pi. And you solve for that and you get 0.096 meters or 9.6 centimeters, which is answer D. Number 25. Boil away 1 liter of water. So you have 1 liter of water. We're going to find its mass and then figure out if you have that mass of vapor, what's its volume. So the mass of 1 liter of water is density times volume. So 1,000 kilograms per meter cubed times a liter is 1,000th of a cubic meter. And so you get 1 liter is a kilogram. Volume then of water vapor is going to be that mass divided by the density of water vapor. So 1 kilogram divided by 0.804 kilograms per meter cubed, and we get an answer of 1.244 meters cubed. Now here's an alternate solution. Volume of vapor divided by volume of water. So we're going to find the ratio of the new volume divided by that 1 liter equals volume, remember, is mass divided by density. So here's the mass over density of vapor divided by the mass over density of water. So we're multiplying by density of water over mass. The masses cancel out. It doesn't matter. We don't even need to find what the mass is. And it just becomes the density of water over the density of vapor. And then you can plug in those numbers and get 1.244. Then you would multiply by the volume of water and get the answer. Next, number 27. For number 27, we want to know what is the ratio of the weight of the uranium divided by the weight of lead. Remember back from chapter 4, weight is mass times G. So we have mass of uranium times G over mass of lead times G. The G's divide out. Now, mass over mass. Mass is density times volume. So let's replace those masses with density times volume. Since we're talking about the same size, same shape, the volumes cancel out, and we're left with the density of uranium divided by the density of lead. You can look those up in the book. I've put these as specific gravities, or if you want them as densities, these are in grams per cubic centimeter. Either way, it divides out to a ratio of 1.69. So the uranium bullet is 1.69 times heavier than the lead bullet. Number 37. If you use water in a barometer instead of mercury, how high would it be under 1 atmosphere? Okay, so pressure equals rho GH. We're solving for the height, so height is pressure divided by rho G. So pressure is 1 atmosphere, and there it is in pascals, 1.013 times 10 to the 5th pascals, divided by the density of water, divided by G, and we get 10.34 meters. So that would be the height of a column of water. This would not be practical in most situations because that's slightly higher than our stadium at Porterville College. That's very large. However, on the plus side, it would have great accuracy because every little difference in pressure would come up as a good distance that could be easily read. Number 41. What is the ocean depth at which a diver experiences a pressure of 3 atmospheres? Just like with the previous problem, we have pressure from the water equals rho GH. Therefore, the height, or h, which is the depth under the water, is the pressure by the water divided by rho g. Now, when I say pressure by the water, that means by added only by the water, the additional amount added by the water. If we're looking at how much pressure a diver experiences, we have to include air pressure as well. So the pressure the diver experiences is equal to the pressure from the water plus the pressure from the air. Now, pressure from the air, we'll take that to be 1 atmosphere. The diver's experiencing a total of 3 atmospheres, so the pressure from the water is only going to be 2 atmospheres. So we plug into this equation, height equals 2 atmospheres, that's 2 times 1.013 times 10 to the 5th pascals, divided by the density of water. We're using seawater here, so 1030, and then you have G. So it's a depth of 20.1 meters. Next is number 44. For number 44, 3 meter swimming pool filled with fresh water. What force does the water exert on the bottom of the pool? Okay, so force equals pressure times area. We want to know what the pressure is. We need to take, just like in the previous problem, it's not just the pressure added by the water, but we have the air that's pushing down on the water. So the water pressure is really, I have here P naught, that's the air pressure, plus rho GH. And this is times the length and the width of the pool. So here's air pressure, the 1.013 times 10 to the 5th pascals, plus rho GH, 1,000 times 9.8 times the depth of 3 meters. Over here I've got the area of the pool. So we can combine these numbers. You'll notice that the pressure added by the water at only a depth of 3 meters isn't that much. Air is about 100,000 pascals. The water is only adding another 29,000 pascals. We plug in all those numbers and we get 4.9 times 10 to the 7th newtons. (51) 70-kilogram parachutist in free fall. Find the buoyant force and compare with his weight. The buoyant force is the mass of the air displaced times G. Excuse me. Mass of the air displaced is density of air times the volume. And while that is volume of the air, that's also the volume of the parachutist. So we have density of air times, and what is the volume of the parachutist? The mass of his body divided by the density of his body times G. Now this equation for buoyant force is going to come up in, I think, 2 other problems after this one. So this is a good equation to keep in mind. So the buoyant force, we have density of air times mass of the body divided by density of the body times G, and we get a buoyant force of 0.84 newtons. Now let's compare that with his body weight. We can say, let's do it as a ratio. The buoyant force divided by his body weight, I call that force of gravity. On the top I have the 0.84 newtons. On the bottom, his body weight, his mass times G. And we get that the buoyant force is about 0.1%. So the air isn't going to do much to float his body up. Next we look at number 52. For number 52, we have a penny released below the surface of a pool of water. What's its initial downward acceleration? So if we released it in the air, we know it would fall at 9.8 meters per second squared. But the water is going to give it a little bit of a floating effect, the buoyant force. So to find that acceleration, we think back to how we did a problem like this in Chapter 4. The net force equals ma, and it's that a that we're solving for. So what is the net force? You look at my force diagram, and I'm going to call down the positive direction because that's the way the penny's going. So weight is down, buoyant force is up, and we have weight minus buoyant force equals ma. Now we start to plug in the values. The weight of the penny is mg. The buoyant force is, and this goes back to number 51, how we did this, the density of the water times volume times g, which becomes density of the water times mass of the penny divided by density of the penny times g. One thing you see is mass of the penny, mass of the penny, mass of the penny. They all can divide out. So the mass of the penny is irrelevant. On the left-hand side, let's factor out g, move it to the side, and we're left with the downward acceleration is g times 1 minus the ratio of the densities. So if there were no air for the buoyant force, it would just be g times 1. But the water versus the pen, did I say air before I meant water? The density of the water versus the penny, that's going to subtract from that 1. So we plug in the numbers and we get the acceleration is 8.43 meters per second squared. Number 54, hopefully very quick and straightforward. Number 54, ice is floating in pure water. What fraction of the ice's volume is above the water's surface? If its specific gravity is 0.931, that means that 93.1% of it is submerged. Now, stating that more mathematically, here's the formula I gave you in class. The fraction submerged is the density of the object divided by the density of the fluid. So 931 divided by 1,000. So we get the fraction submerged is 0.931. So if 93.1% of it is submerged, that means that 6.9% of it is above water, because 100% minus 93.1. Number 55 is very similar. Supposed to be fairly easy. Fraction submerged is the density of the object divided by the density of the fluid. Well, the fraction submerged is 1/2. Multiply both sides of the equation by density of the fluid. So the density of the object is 1/2 times the density of the fluid. Density of the fluid is 1,000, so 1/2 times 1,000, and we get the density of the object 500 kilograms per meter cubed. Number 67. This gets into fluid dynamics. The first part of the question asks to find the volume flow rate. So volume flow rate is the cross-sectional area times velocity. Cross-sectional area, so it's a circular hose, so pi r squared. We're given the diameter, so in place of or in place of radius, we have diameter divided by 2. Remember, it's given in centimeters, so we need the diameter to be 0.0225 meters. Then we're dividing by 2. So this is pi times the radius squared times v. We get a volume flow rate of 1.272 times 10 to the negative 4 meters cubed per second. Now for part B, when we change the diameter, what is the velocity? The way I chose to do this is to not use our answer for part A. I set it up, first of all, with the continuity equation. A2V2 equals A1V1. Solving for V2, we get it as a ratio of A1 over A2 times V1. I've substituted for area, cross-sectional area, that's pi r squared, and you notice the pi's cancel out. So it becomes the first velocity times the square of the ratio of the radii. Now, that's going to be the same as the square of the ratio of the diameters, because look at this intermediate step. If I just multiply both top and bottom by 2, that then becomes diameter. So it's V1 times the ratio of the squares of the diameters, which makes it very easy just to plug in the numbers given in the problem. So we get 18 meters per second. Number 75 involves wind blowing parallel across a window. And is that enough, and these are hurricane winds we're talking about, is that enough to blow the window out? So you can see my picture here. On the inside we have P1, pressure, atmospheric pressure pushing against the window. On the outside P2. And we want to look at the net force. So the net force is F1 minus F2. Force, remember, is pressure times area, so that becomes P1A minus P2A equals area times P1 minus P2. And you'll note I'm actually not solving for P1 and P2 separately as we go along. I'm most interested in just what is P1 minus P2. What is that difference? So let's use Bernoulli's equation. Here's Bernoulli's equation. I set it up to find P1 minus P2. Since both sides of the window are at the same height, I can cancel out the part that involves Y1 and Y2. So P1 minus P2 equals 1/2 rho V2 squared minus 1/2 rho V1 squared. But V1, on the inside of the house, the airspeed is 0, so that'll just go away. And we're left with that the difference in the pressures is 1/2 rho times V2 squared. So 1/2 times the density of air, 1.28 kilograms per meter cubed, times, and I've converted the winds from kilometers per hour to meters per second, 25 meters per second squared. So we get a difference of the pressures is 400 pascals. Now we go down to the equation we first came up with that told us why we need the difference in the pressures, that the net force is area times the difference in the pressures. So we multiply 4.5 meters squared times 400 pascals. And we get 1,800 newtons outward, because the higher pressure is P1. 1,800 newtons, that's about 404 pounds. So the wind blowing parallel to the surface actually does have the ability in very high winds to blow the window out. Number 85. Try that. Okay, number 85. Now we have an airplane emergency exit. There's a difference in pressures between the air from the inside pushing out, I call that 1, force 1, the air from the outside pushing in, force 2, and that's going to be much less than force 1, and we're thinking about what is the force of a pull necessary to pull this door inward. So the net force needs to be at least as much as 0. That's why it's that greater than or equal to sign. So the force of the pull, and by the way, since we want the motion to be to the left, I'm making to the left the positive direction. Force of the pull plus the force 2 from the air minus the force 1 must be at least 0. So the force of the pull must be at least as much, greater than or equal to F1 minus F2. Replace these forces with pressure times area, so P1 times A minus P2 times A. We can factor out the A. So we have A times P1 minus P2. So the force of the pull needs to be at least the area, which is 0.9 meters times 0.5 meters, times the difference in the pressures, 0.75 atmospheres minus 0.25 atmospheres. When I multiply those, I get 0.225, now be careful of the units, meters times atmosphere, meters squared atmospheres. Let's get that in MKS units by converting from atmospheres to pascals. So I multiply by 1.013 times 10 to the 5th pascals per atmosphere. And we get 22,800 newtons, which means one person would need to pull with a force of 5,100 pounds to pull this door inward. The last problem, it's not in the book, it's the aircraft problem given on my web page. Using Bernoulli's principle. So here's my wing, pressure 1 down below, pressure 2 above. Since I'm expecting that there's a higher pressure down below, I'm going to make, basically I'm looking for P1 minus P2. How much is the pressure down below the wing greater than the pressure above the wing? So I'm looking for P1 minus P2. I start with Bernoulli's equation, solve for P1 minus P2. In the next line I simplify. I can factor out the density of the air equals 1/2, and I factored out the 1/2 from these two terms, V2 squared minus V1 squared. Plus, this term I just made go away. If you're curious, you can plug in the values for yourself, make the thickness of a wing, meaning the difference in the heights, depending on what plane it is, no more than probably 30 or 40 centimeters. And if you're curious, you'll find that this value contributes very little to the entire equation. I just made the math easier on the estimate. Just assume it's close enough to 0. It's negligible. So we're really only dealing with this part here. The density of the air times 1/2 times the difference of the squares of the speeds. So we get a difference in pressures. P1 is greater than P2, or P1 minus P2 is 28,864 pascals, or newtons per meter squared. Now the question asks about the force. So we take that difference in pressures, that overall net pressure that's pushing upward, multiply by the area of the wing, which is 78 meters squared, and we get 2.25 times 10 to the 6 newtons, which is about 505,000 pounds. Definitely enough force to keep the airplane aloft.